Okay, we are discussing queuing theory, and queuing theory can have different types of cases. The one which we discussed earlier was that the service and the arrival both are deterministic, okay, and there is only one channel. Going somewhere? Go. Okay, and so in this case, we have equations or rates of arrival or departure, and then on the basis of that we calculate the queue length and the delay and so on. Okay, but the point is length of the queue is what? How do we get the length of the queue?
Difference between two.
Which one? No.
Partial and
Yeah. Arrival and departure. Okay. Difference between arrival and departure. These are numbers and difference between these two numbers. These are equations, the difference between the equations. Okay. And what is the delay? How do we get the delay?
Difference between two curves.
No, that is Q.
No.
Difference between what? The area under the curves. The Q is area under the curve. Okay. Sorry, the delay is area under the curve. So this will give you total delay, and the average is
Divided by number of it.
which number of vehicles? Arrive during what time? Any time? Before what? Huh? Arrive during which time? Huh?
Total time.
What is total time? 24 hours?
No.
The time to clear the queue.
To clear the queue. Okay? To clear the queue. Okay? If you go through the examples, you will find that in some examples we were playing with the numbers. Some examples they were linear equations. Some examples were quadratic or even walaikum assalam, equation up to the third degree. Okay? So the equations numbers can change. Okay? But you have to remember these important concepts. Clear? Okay? So for DD1, the concepts are important. Then we move on to the stochastic case where the arrival and service can have distribution. Distribution meaning there is a probability of different values. Okay? And in this one, we were going through this case which is MD1. Okay? So M stands for what? Markovian. Okay? Meaning stochastic. M follows the distribution. Or arrival follows the distribution. So there is a probability attached with different values for the arrival. Service is deterministic. The way they are going is deterministic, single value for any time. Okay? And number one means number of channels is 1. So first thing we'll calculate in this case is Q intensity, which is arrival rate upon departure rate. Arrival rate upon departure. And if this parameter Q intensity rho is less than 1, then you can calculate average length of the queue, average waiting time in the queue, and average time in the system by using these three equations. In all these three equations, what I need? Rho. Clear? Okay. And what was the difference between waiting time and the time in the system? What is the difference between W and T?
W only in the queue.
W only in the queue. And
G total.
it will include what? Time in the queue plus
Waiting in the queue and after leaving.
yes,
The time for the service.
the service. Okay. And we did this example. Now we have single channel undersaturated infinite queue example where we have MM1 case. Okay. So what do we mean by M1? We know.
One channel.
Okay, what is MM?
Both departure and arrival are stochastic.
Stochastic. Both of them are stochastic. Okay. Now the equations which I showed you earlier, and these equations, and there will be other cases as well. Okay. In these equations, they have already assumed what distribution the arrival and departure is following. Okay, tell me the distributions we know.
Linear one.
Linear, uniform, linear. Okay, where every value has the same chance. Poisson distribution. Okay, we know these two. There's another one. It will be shown in the next page. Exponential distribution. Okay, there's another one which we call as exponential distribution. Okay, so we know Poisson, we know uniform, we know exponential. Okay, these equations are assuming that arrival follows Poisson distribution and the departure follows exponential distribution. Okay, which is how do they know this? Because they did research. Okay, so this is not what normally they follow. Okay, and this is what normally we will follow. Otherwise we will do our own research, right? Got it? Okay, you guys will do it, right?
Yeah.
In senior,
Yes.
come up with new equations, right? With Dr. Mahmood, right? I'll tell you. Okay, clear? Okay, so these equations, when they say that arrival and departure are following stochastic, stochastic must have a distribution behind it. Which type of distribution you are following for the probability? Okay, they already know what type of distribution normally they follow, and they are using that assumption to make these equations. Okay, so there are assumptions behind these equations. My point was, these equations which you see on the board, they have some assumptions. What is the distribution of arrival? What is the distribution of departure? Okay, but both of them are stochastic. They have probability. So you see probability here as well. Okay, so if arrival and departure both are stochastic, the rate of arrival can be given by small q. Rate of arrival, small q. Rate of departure, capital Q. Okay, small q coming, capital Q going. Okay, and both of them are stochastic. Now they are saying undersaturated. Undersaturated means what? What do you mean by undersaturated?
Under capacity.
Under capacity. So that means which one is higher? Tell me. Which one is higher?
Under the discharge.
This one is higher. Okay, departure or service is higher, arrival is less. Okay, so we have undersaturated. Okay, so small q upon capital Q will be what? Less than? Less than 1. Okay. So in this condition, all these equations will apply. Okay. So if you want to find out the probability that we will have n number of units, units meaning vehicles, probability of having n vehicles in the system. Okay. Now what is the system? The queue, the gate, the toll booth, everything is a system. Okay. From the point where you enter the queue till you go away from the booth or the gate, this is the system. All of it is a system. So you may be in the queue, you may be at the counter, okay, but you are in the system. So the probability of having n vehicles in the system is given by this. Okay, so n is here. This power is n. Okay, I think in the slides it's very small. If there's any confusion, you can check it from here. Okay. Expected number of vehicles in the system. Okay, so this equation will give you probability of having any number of vehicles in the system. So you can put n as 0, as 1, as 2, as 3, whatever number. Okay, and this equation will give you the probability of having that number in the system. Okay, this is expected value of n in the system. Expected value means what? If I come or if I look at the system 100 times, which value will I see more often? That is expected value. Okay, if I look at your transcript, you have taken 20 courses, which value will I see more common?
C.
Huh? C, yeah, C. Okay, got it. You got the difference between this one and this one. This one gives you a chance of n. This one gives you the n value which is expected very often. Okay? Okay. Then expected number of units waiting to be served. What do you mean by this? What is the difference between n and n? What is the difference between n and m?
Maybe the expected time.
M are still in the queue.
M are still in the queue. M is still in the queue. N is in the system, so n could be higher than m. If there's a queue, then n will be higher than m. Because some cars are in the queue and some cars are passing. Okay, they are going to the counter or the gate or the booth. Okay, so those cars are included in n. M is only for the queue. Okay. So expected number of vehicles in the queue, then we have the average length of the queue, okay, average waiting time in the queue, average waiting time in the system, okay, and I already explained what do we mean by all these terms. Okay, okay, so then we have probability of spending less than probability of spending t or less time in the system. Okay, that you come. What is the probability that you will get out of the system in, let's say, less than 10 minutes? So this equation will give you the probability of time. Okay, how much time you are spending in the system? This is the equation. Okay. Probability of spending t or less time in the queue. Okay, so this is the probability of spending time in the system, the probability of spending time in the queue. Okay, so this is for time equals to t or less than t. Okay, equal or less. If I want the probability for more, what would I do? 1 minus. Okay, so we calculate this probability. Okay, and then 1 minus. Okay, what else? Probability of having more than n vehicles in the system. That is probability of having n greater than n. N greater than n. Okay. We have an equation for n, right? Probability of having n number of vehicles in the system. Okay. And then we have this one, which is the probability of having n more than n. Okay, can you tell me the difference between them? What is the difference between this, the last one, and this, the first one? What is the difference between them?
First one, probability of n without any condition. But last one there is condition. So
Okay.
it's greater than n.
Anything else?
Better than capacity.
No, no. It has nothing to do with the capacity. The type of probability is different. The type of probability is different. This is probability for what?
N unit in the system.
N, exactly n. This is for exact n, one value. So this is a probability of having that exact value. Okay. This one is having n more than n. So, for example, if capital N is 2, capital N is 2. So small n can be 3, 4, 5 million, 3 million. Okay. So that the previous equation was just for
One value.
one value.
Specific value.
This is for cumulative. This is cumulative. Okay, so that one was individual or distinct. This one is cumulative. Okay, got my point? More than n, any value up to million, up to infinity, the equation will remain the same. It will give you the same answer. Got it? Okay, so this one is cumulative. So capital N is the target we are looking for, and small n is the number of values in the system. It could be anything. Okay. On a given day, 525 vehicles per hour arrive at a toll booth located at the end of an off-ramp of a rural expressway. So they're the toll booth, they have to pay and then they will move. Okay, the vehicles can be serviced by only a single channel, so only one booth, at the service rate of 625 vehicles per hour. Find out percentage of time the operator is free. Okay. Average number of vehicles in the system and the average time waiting for the vehicles that wait. Okay. So 425 is what? Which rate?
Influence.
Entrance. Arrival. And 625 is the service. Clear? Okay. Now they are asking for the percentage of time the operator is free. Which equation should I use? So they are asking for percentage of time, right? So I will have to use one of these P equations, right? So which P equation? There's one here. There are 3, 4 here. Which one should I use? The percentage of time when the operator is free. He has nothing to do. How do I know he is free?
Zero.
Zero. The percentage of time when n is 0. So probability when n is 0. Okay, very good. Let me.
N is zero.
Point 32.
Okay. 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 What are the next thing? What is the next thing? Yeah, the average number of vehicles in the system. Average number of vehicles in the system. So asking for expected value of n, E of n. How much is that? Huh?
2.13.
Okay, gotcha. Okay. 2.13. Okay, so most of the times you are expected to find around 2 vehicles which are in the system. Most of the times. Okay, maybe one in the queue, one at the booth, and so on. Clear? The third thing they are asking for average time of for the vehicles that wait. Okay, now you can see here they have given us the assumption for the equations. arrival follows Poisson distribution, I already mentioned, and the departure follows negative exponential. Okay, so this is the assumption under which those equations are derived. Okay, so don't worry about them, not what we have to do. They are already there in the equation. Okay, and we are just using them. Clear? Okay. So average waiting time. Which one? Which one? Hmm?
First,
Hmm. Yeah, tell me. Okay, the slides which you have, I think these equations are very small, so this is small q upon capital Q. Okay, you can take a picture or write it in the paper. This equation looks very small. So this is small q upon capital Q, and then there's a bracket close, then small q into t. This one, same. Okay, expected waiting time in the queue.
0.00.
Yeah. 0.0034. Now this is hours, right? Because we put everything per hour. Okay. How much in seconds?
12.24.